I'd like to introduce Mark Johnson. He's the Southeast Regional Manager for CalMac. He's been around for 20-some years. He has a BS in Mechanical Engineering from University of Illinois, and he also attended Wisconsin. So please don't give him a hard time for the fact that he has to stand up here behind an ACC sign.
Good enough. Thank you.
He has the shortest bio of everybody that was here, so I lucked out. Didn't have to memorize anything else. He's been with he's been there twice. He took a little break. Resides down in Florida. So with that, I'll turn it over to Mark, and we'll learn about the mic.
How's this for volume? Okay. All right. So first of all, this is not thermal storage. This is accounting 300.
Oh, good.
Oh, yeah, that's funny because you all are staying. That's kind of funny. Got to give you credit for that. I'm gonna hopefully, if you stay with me the whole hour, we're gonna talk about energy storage sort of from a 30,000 foot level, and then we're going to kind of drill down into what it is that we really do at CalMac. So by the end of the day here, end of the talk, you got a pretty good understanding of how energy storage is a part of the energy grid and our buildings everywhere. So these first few slides are from an AIA presentation. AIA is architects. Any architects in the room? Okay, so let's just bash them, really. Let's architects. Are you kidding me? That's a joke. All right. Energy storage. So if you're anybody from Duke here, or okay,
Not Duke Power, sorry.
you know, Duke Power, Florida Power and Light, you know, Progress, which is now Duke, you use fossil fuels to run your power plants, right? Coal, natural gas. Coal is stored energy. It doesn't do you any good until you burn it, right? Oil, gas, gasoline for your car, it's stored energy. When you have breakfast this morning, did you use all that energy right off the bat? No, you store it, you use it as the day progresses. So stored energy is a part of everything that we're doing every single day. Not a new concept. Who's ever driven out to the Midwest or out to Colorado or California and seen all those giant windmills? I grew up in central Illinois on a farm, and I went back to see my old farming buddies last summer, and there's windmills all over their farms. It's unbelievable. I just couldn't believe it. And they have little red lights on them at night. So you used to sit out on the front porch and have a beer and look out over the cornfields and watch the corn grow. Now you sit out on your front porch and have a beer and look out over your cornfields, and you see these flashing red lights everywhere. It wasn't that. I really didn't like it, but they like it because for every windmill they put on their farms, they get $7,000 a year. Not a bad little deal, right? For every windmill. So that's what these are. And then if you think about solar energy as a way to put power back on the grid, is there any storage component to that? No storage component to that. No storage component to wind, right? It blows or it doesn't. It's sunny or it's not. As those two technologies become a bigger part of the energy grid, which they are going to become, albeit slowly, we're going to need more energy storage of one kind or another. And I know Duke right now is spending millions of dollars researching ways to store energy in battery packs, large battery packs at their in the distribution system. How about that guy? Does he know about energy storage? How long can a camel go without water? As long as I can talk. That's a joke. I'm trying to make you nervous. All right, forms of energy storage. In the Carolinas, we're all taking hot showers now. Okay. I'm not anymore because I have 2 kids in high school, but I used to. You have your hot water heater. He's got electric. A couple people have electric, everybody else has gas. or they're not quite sure. If you're taking a shower and you got to heat your water from groundwater temperature around 60 or 70 degrees up to about 110, just one person taking a shower in the morning, you would need 18.3 kW or kilowatts of instantaneous power to do that. Any of you engineers and contractors ever take the cover plate off your water heater and look at that resistance heater in there? Do you know how many kW it is? Somebody here is going to know.
35 to 45.
4.5. 4.5 out of 18. It's 1/4. All right, so now let's think about this. Apply this to your chiller. You got a chiller at your facility. Who has a building with a chiller on it? How many tons of chiller do you have?
Biggest one's 750.
750. Can you imagine cooling that space that you use a 750-ton chiller for with a 180-ton chiller? Because that's what we're doing here. We're downsizing the instantaneous capacity by a factor of 4. That's a hot water heater. Been doing it for, what, how long we had electric hot water heaters? 60 years? That's energy storage at its finest. It's a good thing we don't have 18 kW strip heaters in our water heaters. What would we have on every street corner? Another power plant. Right? Because you have to design for the peaks. If you're at Duke Power, you design for the peak loads. Now here's another thing Duke Power does. Pumped hydro. What's the name of the lake?
Smith Mountain.
Yeah, Jocassee. Did I have that right? Jocassee. I said it wrong yesterday. You guys don't know that one? Duke. It's a pumped hydro reservoir. It puts out about 715 megawatts onto Duke's grid every day if needed. I should say, not every day. They also have another one called Bad Creek. You ever hear of that? These are up in the mountains. They're pumped hydro lakes. So what happens is, got a beautiful lake in the mountain with your cabin right over here. Right? And in the middle of the day, if Duke needs power on their grid, they open up the intakes, let that water flow down through piping, and spin a turbine, okay, at the bottom of that reservoir. And that's going to put out, Bad Creek is 1,000 megawatts, Jocassee, I think, is 700 megawatts. All right? But then every night, you got to pump that water back up to the top of the lake if you want to use that energy again tomorrow. So let's put on our Duke Power hats again. You're going to use power when you let water out of the lake to handle your peak loads. And then at night, you're going to run your base-loaded power plant to put that water back up at the top of that lake. So what power plant, this is for $100, no, I'm just kidding. What power plant is running to pump that water back up to the lake? The most efficient or the worst efficient? The most. So if you're a utility, you have your most efficient plants running 24/7. Those are your nukes. That's your coal. If you have combined cycle, it's your combined cycle. And then you have your least efficient plants running during the peak of the day, because they only have to run a couple hours. Right? This is their least efficient way to produce power. They do it for a couple hours every night. There's also jet engine power plants, gas turbine power plants. Those are the least efficient plants, but they only run 100 hours a year to handle those hot days in the summertime. So that's energy storage at work, and it's right here in the Carolinas, right? But it's not the most efficient way to do energy storage. Anybody ever take a lawnmower apart when they were a kid and go, what's that big metal thing that spins around? A flywheel? That's energy storage. You ever forget to plug your cell phone in? Battery? Next day's a great day, ain't it? You don't have to talk to anybody. No, it's not like that. So what we do is thermal energy storage. And instead of storing power, we're storing thermal energy storage. And in our case, it's specific to the use of the building, and it's for air conditioning. All right? When you use a chiller, what's your heat transfer fluid? Water. Water is the best heat transfer fluid known to man. It's spectacular. There's nothing like it. As soon as you start messing with it and putting glycols in it or phase change materials in it to change the freeze point, it loses its capacity. Okay? Water, pure water is spectacular. So anybody that does ice storage uses water as the medium to store the energy. And that's what we do. So that's a cutaway of one of our tanks. It's not to scale. So that's 8 foot tall, and that's 7.5 feet in diameter. And one of those tanks is about a 20-ton chiller. Okay, so you put it in perspective for your building, you need about 49 square feet for a 20-ton chiller, 7.5 by 7.5. All right. I'm going to get more into that in a second here. I don't want to do those yet. I want to show you this one graph, and then I'm going to move on into some more things about thermal storage. This is interesting to me. So this is the wind generation output of a wind farm in California. And what you see is the real-time production of that wind farm. All right? Yeah, that's the blue line. The red dots are when that particular utility peaks. Do you see a problem? So the utility spent money to build a wind farm that can produce 1,000 megawatts. But when they need the power in the middle of the day, they're getting around 200. That's not a very good investment, is it? So if wind's going to work, it's got to have storage of some kind. Battery storage on the grid, people using energy storage in their facilities, but it just doesn't. This is not good. And that's kind of true of most of the places in the country where there's these wind farms. It blows a lot at night, not as much during the day. It's kind of counter to what you're trying to accomplish. All right, that's enough about all that. I got to get to another presentation. All right. So I want to talk about this technology from your point of view, or from an owner's point of view. Because if the owner's not happy, we don't sell anything. If you're a contractor, you don't get to install anything, nothing happens. So we want to make sure that our owners are happy. These are 4 different types of owners, building types: a school, a retail store, that's a Costco, the Bank of America Tower in New York, and that's the University of Arizona. These building types are all very good for ice storage. What do they all have in common? Anybody think about that?
They don't run at night.
Yeah, there's not a lot of load at a school at night. Costco's not open. This particular one's not open 24 hours. The people that work in this building aren't there 3 shifts a day. They're only there 1. And the University of Arizona peaks during the day when all the kids are in school, and at night, it's the desert. It's nice and cool, and everybody's back home. All right. So we're going to talk about why thermal energy storage is used, why it's popular. From an owner's perspective, what are you facing when you add this to your plant? And maybe show you some case studies and get out of here. So the biggest reason that I'm in business, our company's in business, is economics. All right? You guys you own buildings. You're trying to wring out the operating costs. You're trying to have that building run as inexpensively as it can. Well, utilities, and just about every utility in the United States, charges you more for their energy during the day than they do at night, even if they don't tell you they are. And that's part of the message of today's talk. I'll give you some examples of that. Green power needs it. When I say green power, I'm talking about those instantaneous power sources like solar and wind. You got to have storage if those technologies are going to work. All right. If we didn't have a good return on investment, nobody would buy our equipment. So we have to talk about that. If you're trying to get lead silver, lead gold, lead platinum, you got to find a way to beat. Is it ASHRAE 90.1 now? How do you do that? Well, this is one of the technologies that helps you do that in terms of lead points. You want to increase your central energy plant flexibility. If you have a means of storing energy for your chiller plant's going to run more smoothly. It's not going to have to follow the loads up and down instantaneously. It can run smoothly. The chiller can, because you've got that storage component. All right. So here we go. First things we want to talk about electric rates. Who's old enough to remember blue light special? Kmart. All right, got a few blue light special people. Did you have to go to Kmart in the middle of the night to get a blue light special? When I was a kid, my mom took me in the middle of a perfectly sunny day, and I hated that. But she got to get her blue light specials in. There's a blue light special on electricity every single night, and I want to show you how that plays out. So, you guys know the difference between energy and demand? Energy is kilowatt hours, right? Demand is kW. So demand is your peak energy consumption whenever that occurs in kW. So this is a typical demand rate of $10 a kW, and it doesn't matter what time of day you set your peak, you're going to pay $10 a kW that month. So this is a non-time of use rate. This is Progress LGS right here. All right. Progress now Duke Power. It's also confusing. And then you're paying about 5 cents a kilowatt hour for energy. So your power bill is a function of your demand charge and your energy charge. All right. Now, you got a building, and you use energy in a curve like this, right? You don't use it flat all night long typically, like a hospital would, but most office buildings, schools, universities, churches, you're going to use energy something like this. All right, if you could take that curve and squish it, all right, and you can make it look like that. For $200, just kidding, would you save any money on your power bill? You're not saving any energy. You get your power bill at the end of the month, and it says 20,000 kilowatt hours. This guy was 20,000 kilowatt hours, that guy was 20,000 kilowatt hours. Did I save any money on my power bill? I got a yeah over there. Okay? You bet you did, because you dropped your billing demand. Okay? At $10 a kW in this example. That's what we're trying to accomplish. So, I want just to drive this home a little more, because I think this gets missed a lot as we are designing chiller plants for the future. What's it really cost per ton to operate for a summer month? All right? And here's an electric rate at 7 cents kilowatt hour, $12 a kW. That's a very typical sort of rate. And we're looking at an air-cooled chiller at 1.2 kW per ton. If we operate that chiller about 160 hours a month, our energy charge is going to be $13.40 that month. If we operate that chiller just 1 hour and it sets our peak demand, will the chiller set the peak demand? Well, heck yeah, well, it's running in the middle of the day, all right? $14 for the demand. So you may think you're on a power rate of about 10 or 12 cents a kilowatt hour. You're not. You're on a power rate of 7 cents a kilowatt hour, $12 a kW. Your demand, I'm getting dizzy. Okay. Your demand is 52% of your bill with this example. I don't know if you thought about this or not. So if you could cut your demand of your chiller in half. So the kW that your chiller's drawing at the peak of the day, if you could cut it in half, you'd cut your power bill for your chiller, at least your chiller, by 25%. This is the whole gist of using energy storage in your chiller plant. Anybody with me on this so far? All right. You guys are quiet. You need to stop and get some coffee or something. Come on. Raleigh, I gotta tell you, Raleigh was a lot more active than you guys are today. I'm just kidding. All right, they were. All right, so here's some power rates around here. Around here. There's Duke OPT. Are you on that rate at the depot? I think so.
Not sure.
Yeah. Duke OPT is 15 bucks a kW in the summer, 9 bucks a kW in the winter, 6 cents a kilowatt hour on peak, 3 cents a kilowatt hour off peak. So, is there a reason there for you to reduce your billing demand? Yeah, 15 bucks a kW. Is there a reason there to use more energy off peak than on peak? You betcha, it's half price. Who's got kids? Tell your kid, if they're driving yet, I'll say this. Tell your kid, that doesn't work, does it? Ask your kid, no, you gotta tell them. Progress LGS, 11 bucks a kW, 5 cents a kilowatt hour. That's expensive. That's expensive. There's a reason to keep that down. Progress SGS TOU, we have a nice project at Cary Academy in Raleigh. This is the electric rate that they use. We want to take demand out of that time and energy out of that time and put it into the off-peak. Duke Power G rate, $3.60 a kW. Guess what that is? Cheap. That's crazy cheap. This is not an electric rate that would drive you to use thermal energy storage in your chiller plant. All these other electric rates are. Does that make sense? Right? The savings, because it's so cheap for demand here, really isn't going to drive you to it. There may be other reasons why you might use thermal storage. Chiller plant, smoothing of the operation, backup capacity. Maybe you're going to add some load. You use ice for that, but that's not something that's going to drive it to use thermal storage. There's a look at the demand for Duke's OPT, 14 bucks and change on peak, free off peak. And there's your energy charges, all right? All right, so one more time, and I'm kind of beating this to death, but I think it's important. If you could use a kilowatt hour during the day versus a kilowatt hour at night. Okay. Kilowatt hour at night is going to cost you 7 cents for the rate that we just talked about. Right? Kilowatt hour during the day, you factor in that demand charge, and you're looking at 13 cents. You're half off at night. So now we get to your kid. Your kid, my kid's Tanner. Tanner, do me a favor. Take the cars to the gas station tonight and fill them up with gas, because Mobil is running a half-off sale. Would you ask your kids to do that if Mobil was running a half-off sale at night? Well, heck yeah. You got an opportunity to do that with your chiller plant. It's right there. All right? Half off. That's why we got thermal storage down at the depot. That's why you got thermal storage at your facility. You take advantage of this, it's huge, huge savings for the amount of energy you can shift off peak. All right. Okay, I need a little crowd participation. And I'm going to go to this side of the room, because you look the most promising. I've got a couple answers from the guy back there. Please use nitrates in a sentence. Please.
Night rates are cheaper than the day.
Do you know who that is? Do you guys over here know who this is? He's an accountant. He gets it. It's about the money.
There you
Nitrates are cheaper than day rates. That's the bottom line. So use them. Right? Use them. All right. So you're an owner and you believe what I just told you. You've talked to Duke Power and they've told you the same thing about the rates. Now we gotta get into your plant design. You don't want a plant that's got a lot of maintenance. You want a reliability. You want a plant that's pretty easy to operate. You want a plant that's got a decently low first cost so that you'll buy it because you don't want to spend a fortune and not get a return. Let's see what we can do here. All right, so with the product that we build and sell all over the world, the thermal storage vessel is made out of, first of all, no moving parts. Is that a good thing? That's pretty good. It's made out of nothing that can corrode. That's a pretty good thing. It's made out of the most ductile plastic that we know of for building construction. That's polyethylene. Right? Polyethylene piping is what's used to transport natural gas all over the country. All right? So polyethylene, nothing that can corrode, no moving parts. Pretty good story as it relates to maintenance and taking care of a piece of equipment. We estimate that our tanks are going to last 40, 50, 60, 70 years. Okay? That's pretty good, ain't it? What do you got to do? You got to add a 16-ounce bottle of biocide every 2 years. If you don't, you'll be fine. But that biocide is to keep growth from the inside. What grows at 32 degrees? Not much. So, and the water level, you may get a little evaporation, and you may need to add a little water to the tanks every year or so. That's about it for routine maintenance. Let's get into the battery a little more. Here's a cutaway which I had up here a minute ago, and there's the heat exchanger taken out of the tank. A lot of people ask me, they say, that's a good idea, Mark, but there's no way I got room for this stuff. It looks really big. How much space do I need? Well, think about it this way. If you have 100,000 square foot space you're trying to air condition, you got to find about 800 square feet somewhere outside the back, in the parking lot, in the basement, on the roof, about 800 square foot for the tank farm. So it's less than 1% of the conditioned square footage. You need space for that somewhere. All right. This layout right here is 22.5 feet by 22.5 feet. It's going to give you around 180 tons of cooling for the afternoon, just to get an idea. Okay. We also make a 11-foot tall tank, about like that, it was really built for our Manhattan, New York City market because we put the tanks in the basements there. You know how many story basements they have in Manhattan? It's like 5 or 6 stories on most of those buildings. So that's a great place to put the ice. Reliability, pretty good. We had a problem on a job here. We fixed it, right? We had a little leak. We fixed it. What do you do when you have a leak? In our systems, you have 56 circuits, all right, that you're building ice on. If you have a leak in one of these tubes, you simply plug that tube here at the header, and you've lost 1/56th of the capacity of your tank. That's about it. All right. See if I get you on this one. We tried to take the Gene Simmons approach. I got these guys a little bit. KISS. Keep it simple, stupid. We try to keep the operating of our plants as simple as possible. If it's not simple, and if you can't do it, if I can't explain it to you in 10 minutes, it's maybe too complicated. So let's try to keep this simple. Basically, most plants have 2 modes of operation, some have 3. And I'm going to talk to you about each of those right now. Making ice, of course you got to recharge your battery every night, and then cooling. And you're going to either cool with the chiller, with the ice, or with both. All right? Ricky, do you guys cool with ice only sometimes?
Full storage at depot and partial with the other.
Yeah. So here's a plant layout. This is a building that's got a 400-ton peak load, concept that I've been talking about so far is this partial storage. There's also full storage. I'm going to talk to you about partial right now. That's 400. Think about the water heater for this example. Right? Think about that water heater. 400 tons, but we only have 220 tons of chiller. Okay? Water heater would have been 18 kW, 4.5 kW. Same idea. The compressor is much less than the peak tons. So in the morning, at our office building, the load ramps up. Everybody starts coming to work, getting their coffee, settling into their desks. Or if they're at school, they're getting ready to go to school. We set the chiller at 44 degrees because we want 44 degrees going through the load. There's a modulating valve around the ice tank farm. It's also set at 44 degrees. So as long as the building load is less than 220, in this example, ice doesn't get used. Does that make sense? So think about the loads ramping up in the morning and the load comes up to 220, and all of a sudden, this chiller can no longer produce 44 degrees because it's not big enough. Right? It's been downsized a little bit. As soon as that goes to 44.1, this modulating valve is going to work because it's looking for 44. So it's going to let flow go through the ice tank farm to give us our 44. All right? So it's like chillers in series. This one you load up first, this one you load up second. Okay?
Which one use the ice first?
No. Yes and no. The goal of an ice storage system is to flatten the load. It's to flatten the kW on that the utility sees. You bring that chiller up to 220 and it's running at a nice flat load. What's the peak? 400. I'm going to let the ice get the peak. All right? This is a partial storage facility. So partial means chiller first, ice second. So that's typical cooling during the day. The control sequence hasn't changed all day long. This guy's been set at 44. This guy's been set at 44. That's all you're doing. Just cooling the facility. All right? Just the occupants don't know if it's coming from the chiller or the ice. They don't care. Okay. Any engineers, design engineers, mechanical engineers in the crowd? There's one. This chiller operating at 52 degree leaving temperature in the peak of the day versus that chiller operating at a 44 degree leaving temperature. What do we know about that chiller's performance at 52 versus 44? It's more efficient at 52. It's not having to do as much work, right? So not only is it downsized and putting less demand on the billing meter, it's also most efficient when you want it to be the most efficient. When that energy is costing you twice as much. All right? That's the whole concept here. All right? That all good? Every night, you got to remember to plug your cell phone back in. So that's what I'm going to show you here. At about 10 o'clock at night, people have gone home. It's off peak if you're on a time of use rate. You tell the chiller to recharge the battery. And all that means is let that chiller run as loaded as it can. And it's going to run at approximately these temperatures. And that 25 degree glycol and water solution is going to go through those tubes and it's going to build ice. And that's going to take between 6 and 9 hours typically, depending on how much ice you used the night before. When this temperature right here is about 26 degrees, what do you guys use? Right here, that shut-off temperature.
28 return.
28. When that return temperature is in the 26, 28, it depends on the chiller and ice combination that we have. We're done making ice. Because what do you know about water, right? The water, it has a latent heat of 144 BTUs per pound. So for it to change phase from water to ice, it's 144 BTUs per pound. But once it's ice, there's no load on. There's no load there. All you do is try and cool the ice down cooler. So as soon as that load goes away, when you have the phase change and go solid ice, these supply and return temperatures just drop. So we're just looking for 26 to 28 degrees here or here, and we're done. the green bar on your iPhone is filled up. That's the idea. All right. If first costs weren't reasonable, we wouldn't have anything to talk about. I couldn't compete with chillers because my competition is chillers. Sorry, Terrain. That's how it works, right? If you just look at the tonnage of the load. So on a dollars per ton basis, storage is maybe 10 to 20% more than an air-cooled chiller dollars per ton. If you're just going to buy a tank and stick it out in your chiller plant, that tank in a dollars per ton basis is a little more than an air-cooled chiller. But this tank for the next 50 years is going to save you around $2,000 a year. Okay, so it's not a bad investment. Simple paybacks for partial storage, like I just showed you, with Duke's OPT rate, with SGS TOU at Progress, with the LGS rate with Progress. We ought to be, certainly we're less than 8 years, we're probably in the 3 to 4 years simple payback range. All right, is that a good payback? Ain't bad. What are you guys earning on your CDs these days? This is a decimal place better than that. Guarantee you that. Maybe more than that. All right. So here's a little sizing example. A high school. What's a high school in Greensboro? Peak cooling load. Anybody got an idea? We do look at a high school lately. I know there's a lot of schools high schools that peak around 400 tons because we did a lot of them. A lot around that size. So I used an example. If you've got a building that's got about a 400-ton peak cooling load, if you're going to use ice, you're going to have to get a handle on how you use the building. You're going to get a handle on when do the kids come to school? Is that an easy question to answer? Pretty easy. When do the kids go home? Is there a PTA meeting at the middle of the night? Is there a basketball game that night? We're going to know what you're doing in your building. And we're going to size for that. Right? Worst case. So here's a cooling load profile. Everything gets shut down around 10 p.m. With thermal storage, what we're trying to do is run our chiller over here, and then have it run flat loaded all day. This is partial storage. And they're going to have the ice get this load. Why? That's the most expensive power, right? I can sort of beat that dead horse pretty hard. So here's a case where we had about 8 hours at night to recharge the batteries, and we're able to shift about 180 tons of load, about 40%. So that's a good thermal storage application right there. If that load would have been flat for 24 hours, probably not a good thermal storage application. If it had been an elementary school or a church, spectacular thermal storage application. Why? Because on those kind of buildings, that demand charge is even a higher percentage of your power bill. Because you don't use a lot of energy, but you set your peak for 3-4 hours. So here we go, we're in Duke Power territory, and we're going to do this to our building. Well, here's the good news. Duke Power has rebate money for this technology. All right, and it's significant. In this case, it's $190 a kW with Duke. So we look at how much load we're going to shift here. What's that in kW? Take it times 190. In this job here, we're going to get a $42,000 rebate check from Duke right out of the box. All right. They just wrote a check for the Winston-Salem firing range. I don't know if you guys ever heard of that facility. I've not seen it yet. Talking to a guy today who's been there. But there's a firing range in Winston-Salem that's air conditioned. And they're shifting about half of this load. They got a rebate check in the, I'm sorry, less than half. 50 or 60 kW, it's pretty small. What are you doing this for? You're doing this to save peak demand. In the summer, you're going to save around $12,000 a year in demand charges. Is that significant? Is 12 grand real money? I think so. In the winter months, so like winter by Duke Power is defined by, April, May, the shoulder months, and all the winter months. You still have cooling. The demand charge is less, but we're still going to save money. And we're looking at about $5,000 a year in savings in the off-peak or winter and spring and fall months. In this example, compared to air-cooled chillers, a smaller air-cooled chiller and ice, we're going to save around $17,000 a year in power bills. Okay. That's about $100 a ton shifted a year. And that right there is a good rule of thumb. If you're between if you're at $80 a year and up in savings, we probably got an opportunity that's going to pay back. If it's cheaper than that, then maybe not. So what's that savings driven by? It's driven by the demand charge, and it's driven by the load shift. So you've got to design with those two things in mind. All right. That's a lot of money. So if we could shift to 700 tons of load, 700 tons times about 100, you're looking at $70,000 a year demand savings. All right. There's always a payback to this. I'm not going to tell you we can do ice and chillers for the same price as chillers. We can't. We can come close. So there's an adder. And in this example, the adder might be about 50 grand, might be 60, might be 70. It's in that ballpark. All right. If you're saving $17,000 a year and you're having to add $50,000 to $60,000 to your first cost, that's a simple payback, 3 to 5 years. So from an owner's perspective, is this a payback that you can get excited about? Can you pitch this to your money guys? Would you do this in your building? Okay. Where's the right applications and where's the wrong applications? This is important. Our technology is based on chillers. We're not a DX type. You know, this isn't light commercial. So if your building has a chiller, this is a technology you want to look at. We don't do residential like commercial. We're always looking for time of use rates or demand charges, $10 a kW and up. All right? And you have that here with Duke, with the OPT rate. We're looking for cyclical load profiles, so a building that's off at night, on during the day. So what's that? Schools, churches, auditoriums, offices, shooting ranges apparently. I never ever thought about that. When's the right time to look at this technology? When your chillers are being replaced, or when you're building a new building, and when you're adding load to an existing facility. So the important takeaway from that statement is, this is not a technology where you're going to go, hey, I got a perfectly good working chiller plant, and I want to add some ice to it. And I want to make that an energy project. That's hard to do. It's on the outskirts of what's acceptable for an ROI. Simply because to make this ROI really look good, you're usually going to downsize your chillers a little bit. All right. Now, the Duke rebate helps, and it'll help make full storage maybe the higher end of our payback range, maybe 8, 9 years. Without the rebate, you certainly wouldn't do that. Okay, did all that. Wrong application. Just, you're not going to add ice for the sake of adding ice. Flat load profiles doesn't make sense because I might set a peak at night making ice. And if I don't have a time of use rate, I'm not saving any money if I'm setting a peak while I'm making ice. Here's some pictures, and I'm sorry I don't have any local photographs here, but the tanks look the same here as they do in Atlanta or in Colorado. This is an office building in Marietta, Georgia. That's a 110-ton chiller. That's about 80 tons worth of ice or load shift. So that plant right there is about a 200-ton chiller plant. All right. Anybody like to vacation in Colorado or Arizona where it's real dry? You just know humidity, right? So I live in South Florida, but it's, man, the summers you don't want to be down there. It's hot and sticky. But you have to design the chiller plant for a high school for June, right? Or September or August. High school in Florida, 250,000 square foot high school, it's about 1,000 tons of chiller capacity. 250,000 square foot high school in Fort Collins, Colorado. You know what the peak load calculation was for this job? About 250 tons. I just freaked out when I saw this. I couldn't believe it. I'd rather sell chillers in the southeast than I would than in Colorado. So at this 250,000 square foot high school in Fort Collins, there's a 140-ton air-cooled screw and 8 CalMac tanks. That's been there for about 10 years. But that's a nice picture of the plant. Very typical sort of air-cooled chiller and ice plant, both of these. A lot of times you got to be creative on where you're going to put the storage. This job, the owner didn't really want to look at those tanks. Now, I think they're beautiful. But I'm the only guy in this room that thinks that. So what they did is they buried them to about here and poured a concrete pad. And now the tanks stick out of the pad about that far. Right. Then they built a nice little brick fence around the yard. This guy here completely buried his tanks. And then he put wood chips over the top. This guy here didn't have any space out back, so he built a rack on his roof to spread the weight to the load-bearing columns and put the tank farm on the roof. Right. How about these guys? So this must be California or someplace where there's earthquakes, right? Because that's an earthquake restraint. And then this guy, this is the University of Arizona in Tucson. And the University of Arizona takes most of downtown Tucson. I've never been out there. They have 4 different chiller plants around Tucson, all linked together. But there's just no real estate there. It's an old city. It's all built out. So what they had to do for their plant is their storage is the double-decker. And they have two of their 4 plants have tanks double-deck like that. They shift around 25,000 ton-hours a day. The connected load of their chiller plant is 50,000 tons. How about that? That's big. But because of diversity, they think the peak load's about 30,000 tons. Of the 30,000 tons, the CalMac tanks shift about 5,000 or 6,000 of that every day. Yep.
So when they did that at the University of Arizona, they didn't use their existing chillers. They bought new chillers just to charge those tanks, right?
In this,
Or did 40 or 42, 30?
yeah, so in that job, it's a large job, it's all water cooled. So when they went to build this plant, they put in new water cooled centrifugals that were capable of making ice.
Right.
Yeah. And I think there's 4 or 5 at this particular one, all around 1,000 tons. So that's just some ideas. But most of the time, the tanks are just sitting outside on a concrete pad. We have over 3,000 installations around the country. Florida's a big market just because of the utility rate structures and because of the temperature. There are over 100 systems down in the Carolinas. So this is kind of taken off. Most recently, for us, Charleston has been a pretty hot market. Myrtle Beach, the demand charges in Myrtle Beach are $18 a kW. That's high. Columbia, we've done a few new high schools around Columbia. Demand charges there are around $16 a kW. What's the junior college we just did, Randy? Randolph Community College. Yeah. And I don't remember the demand charges. I think around $10. It's a progress customer, I think. I do have a story I'd like to share with you. What time we got? About ready to go? 5 till. All right. So one of our other businesses is ice rinks. Does that make sense, right? We know a little bit about ice. And we have a chiller plant, train chillers and thermal storage in Rockefeller Center in New York City. And we've had it there for 5 or 6 years. And they like it. They're very happy with it. You ever go to New York City in the winter or know anybody that went up and got to skate on that rink? I never have, but I'd like to do it one day. That rink is 70 years old. And the steel coils that they used to run salt water through at 12 degrees to build ice on the terrazzo floor, that's how they did it. They froze a terrazzo floor and built ice on top of that. Okay? It finally failed after 70 years. So how about that for some good engineering, right? The Tishman Spires building manager for Rock Center wakes up Thursday morning to find out that he can't get ice on his rink. If you don't have ice at the rink at Rock Center when you're supposed to have ice at the rink at Rock Center, you're in big trouble. I mean, it's not a big deal to me, not a big deal to you guys, but if you're there, it's a big deal. They called our company because they found out we did ice rinks. And they called Mark McCracken, who's our CEO, and they go, look, come on down and take a look at this rink. Mark lives in the city, so he goes down to look at the rink, and they go, take a look here, what do you think? Mark's been building rinks since 1976. Matter of fact, he said he built one here in 1976. So he might talk about it today during his talk, when he was a young man. The Tishman Spires guy looks at it and goes, what do you think? Are we screwed? And that wasn't the word he used. And Mark goes, yeah, you are. You're not going to get ice on this rink. Tishman Spire guy goes, do you have anything where we could get ice built on this rink? Mark McCracken goes, yeah, we could probably do something. Can you have it done tomorrow? And Mark says, yeah, we can have it built tomorrow. So, can you have ice tomorrow? Mark says, no, that's not possible. We can have ice the next day. So this is Thursday. So we shut down our factory, quit making the tanks that I sell, built the rink, sent half a dozen guys down to Rock Center, measured it all out, built the rink, laid it out. Saturday night, they had ice. So now, if you ever see the Rock Center ice rink on the Today Show in the morning when you get ready for work in December, that's our rink. Thanks to Mr. McCracken, who was not asked what it would cost to get that rink put on there. They just needed to have it. So that's kind of cool. All right. Some case studies. We got over 40 schools in Sarasota County. They have saved, when I did this slide, over $8 million in demand charges with our product alone. That number now is probably around 12 to 15, because that's an old slide that I did around that time, 2008. They document it. They know what they're saving with ice. That's a lot of money. So every school they build's got ice on it. Hillsborough County is Tampa. So they just started getting into ice, and they're doing partial storage on all their systems. Sarasota does full storage. These guys have done about 10 schools in the past few years. Actually, we've got 11 there. A typical elementary school for them is like a 250-ton peak load. We'll put in around 180, 170 tons of chiller and ice to satisfy that. All right. Johnson County Schools did a bunch of schools with us back in the 90s and early 2000s. A little over 20, I think, is the number. I don't really know exactly what it is. Never had a rebate over there, and that's a typical school over there. Tanks are outside on the concrete pad. City of Charleston just did a couple. Bottom line is this stuff, thermal energy storage, the way we do it, it's pretty simple, pretty easy to control. We've been around since the late 70s. We're going to be around a lot longer. And there is an ROI to this stuff. You design it right, set it up right, and know your electric rates. That's the key. And I'm about done. I appreciate you guys sitting with me the whole dang time. Any questions?